Okay, well, we received the Fluke 1953 in Connecticut. Um, Packaging looked good. The handle, unfortunately, was left up against the top of the case and got pressed down in there, so I got a couple of nicks on the edges where they got compressed in, but I can live with that. The foot that was broken, Bob reported broken when he received, is here in pieces. I took a foot off. It came off of this front left corner. The foot has a detent in it, which is used to hold the unit upright with the handle. I'm not quite sure. Took the foot off of the rear left, moved it forward so that we can more easily see this result. So I've got the unit on. It's been warming up for a little while. Bob was reporting that channel A and B, I believe, were okay. I will double check my report from him, but channel C, he said, was touchy, that it was bouncing around. We're going to check that out. So, all right, we got 50 megahertz showing on channel A, which is 50 coming in. That's good. The channel sensitivity is about 22 millivolts. Got plenty of signal. I could attenuate it. Okay, and we see that we don't, which is expected, because this is right at the limit of its sensitivity anyway. And we should be good up to 125 megahertz on channel A. Let's okay, according to specs, channel A at 125 megahertz requires 50 millivolts. And I've got a 50 millivolt signal on here right now, and we are reading 124.999.94 kilohertz, so 125 megahertz. The HP is putting out 125 to 3 digits, so we have better accuracy than that, and we're in lock, so we're holding it relatively steady at the generator. And if I compare that to my Philips up here, see how it's doing. 99945, so right on the money. So that's looking good. Let's check the signal strength. "54 millivolts." So that's close enough to 50. So I'll buy it. It looks good. Let's take her down. All right. I'm at 500 kilohertz on the HP. I've got 500 kilohertz showing here. Kilohertz, right on the money. That's looking good. It's stable. That's good. Channel A looks good. Now I believe he said channel A looked pretty good to him too. We're going to check channel B. Checking the specs off of the manual. Channel B, 30 millivolts from DC to 25 megahertz, 100 millivolts. Let's see. Well, that's it. That's the entire range. If you're measuring a sine wave, it's 30 millivolts to 25 megahertz. It'll handle a 100 millivolt pulse. Anyway, that's channel B is primarily used for establishing ratios and so on against channel A. Channel B is used to establish ratios against channel A. So, all right, I'm using both channels A and B. I'm in the frequency of A to B position for my function switch. My frequency of channel A is 100 megahertz. We can check that. Let's see. Okay, A is 100 megahertz. And frequency of A relative to B is 4 point and then 4 zeros. Well, 4 goes into 100 megahertz, 25 megahertz. So I'm reading 25 megahertz on channel B, and 25 megahertz is the rated limit for channel B. So I'm seeing stability here. I'm relatively happy with the way that looks. All right, let's get back to A, and let's just take her down. This would be 1 megahertz. All right, it looks good. We're in a 1 second position. We got 1 megahertz right down to the hertz. Okay, we got 100 kilohertz coming out of now our HP frequency, 3320 frequency synthesizer, which is low RF to audible. We're going to take her down now to 10 kilohertz. There's 10. That's good. 1 kilohertz. Yeah. 100 hertz. 10 hertz. Okay. And 1 hertz. There's 1 hertz. Okay, we're gonna go back from here. We'll go to and we gotta have at least 50 megahertz. 50. All right, and we're running about 56 millivolts right now. Getting nothing on C. This isn't good. Let's increase the power. That's. I'm getting nothing on C. All right, let's try a higher frequency. It's 100, 50. 250, 350, 450. I've got a reading on 450. Looks like we've lost our low end on channel C. And what about the sensitivity? Yeah, we lost sensitivity as well. I'm having to pump. Let's see. We got 102 millivolts. $102 millivolts. So I'm supposed to have a sensitivity of about 15 millivolts minimum. So something around 20 millivolts ought to be able to pump this thing, and we're running 5 times that much in order to get a signal in here, and our frequency is way up. If I try and take her down, I can get 390, 380, not without increasing power. In fact, it's just not doing it. 380. 70, 60, and then she dropped out. And we're running quite a bit of power in there, so there's something definitely wrong, channel C. We're not getting anything below 360 megacycles, and it doesn't matter really how much power I put in here, so we're going to have to open this thing up. Alright, I've opened the unit up. I don't see any signs of visible damage. No charring or anything. Alright. I'm going to have to kill the power and remove the 1 gigahertz board out of here, and we'll take a look and see if we can figure out what's going on. Removing the power. Okay, power's dead. I'm going to set this camera up in a little tripod. Alright, I'm going to remove the board. Stubborn a little bit. Don't know how long it's been since the board's been. Oop, there we go. Alright, the board is out. Alright. And I'm going to use this mascometer. I'm going to start testing the board, see if I can figure out what's going on. Alright. Since it's lost its low end, my first thought, and its sensitivity, my first thought would be capacitors having changed. Alright, this tantalum is reading 10 microfarad, and that's what it is. It's a 10 microfarad, so that looks good. Let's try reading this diode. 0.293, it says it's a diode. Let's try it in the reverse. One point something. That looks good. Two, 3, 5. And in the reverse, 1.84. That looks good. So decoupling capacitors, that wouldn't be it. Let's take a look at the schematic for a moment. All right, looking at the block diagram. Looks like C6 here could be a problem. I could check that out. I don't see another capacitor really used as a feedback element. We're going to check that fuse. We have the signal coming into a fuse, then we go to the amplifiers. The rest of it's feedback. C6 right there. We'll check that out. Yeah. C6. Getting an odd reading on the fuse. Looks like 52.7. Reading like a capacitor. It's reading in nanofarads. 52.8 nanofarads. That's odd. We have a spare fuse right on the board. Let's measure it. 0.3 ohms. Well, we're definitely not getting that reading on the fuse. All right. The signal comes through this line here. I'm assuming you can see this. I'm not positive. Signal comes in here. The first thing it hits is the fuse. That fuse is blown. When I compare it to the spare fuse on the board, I got continuity on the board and a 0.3 ohm reading, and I'm getting on that input a reading like a capacitor. It says 53 nanofarads. So at real high frequencies I would be able to get through that capacitance, but at low frequencies I wouldn't. So let's remove this fuse. And replace it with the spare. Alright. See what our reading is now. Continuity. Alright, let's let's reinsert the board, and we'll try her out again. There'd be a very good reason this board would not have worked. I think we got that back in there. Let's try powering it up again. All right, power's on. That should be 50 megahertz. And what do we see? We're coming in on channel C. Function is C. We have 50 megahertz coming in. We're reading 49,999.94 kilohertz, so 50 megahertz. Relatively stable. She's climbing a little bit, but since I had the power off, probably warming up a little bit, so I'll have to check stability after this, but it looks like I'm now getting my low frequency through. That's after the removal of this tiny little fuse. And that fuse is right on the input, so the signal from the outside world coming in on the C jack goes through that fuse and feeds the rest of the circuit. If that fuse is blown, it's blown because the signal exceeded the 5 volts that was printed right here on the front. It says 5 volt RMS max, and if you read the manual, you'll also be warned that there's a maximum on this. You're limited to 15 millivolts up to 5 volts, 50 megahertz up to a gigahertz. We're reading 50 megahertz, right on the money. Let's see if we can kick her up. There's 100, 200, 300, 400, 490, 499. We're going to have to switch generators in order for me to get higher. Okay, the doubler's there. And take off our lock. Kick ourselves up here to... Alright, we're showing 200 on the HP. 200 on the HP. We're showing about 400 on the Fluke. Coming through the doubler. And if I compare that to results on my Philips here, 400.0083 or 4, somewhere in there. Last couple of digits are flaky because I'm not locked. 400.008. Okay, that looks good. Let's go ahead and raise her up. Alright, we should be reading 800 on here now. And we'll take her up to a gig. Alright, we should be reading a gigahertz right now. Alright, so we got 999.9999, a gig. We have a little flutter on the last digit, but just about any generator you operate from is going to have a little bit like that, even though we're locked. Looks good. If I compare that to my Philips, $999.999998, right in there. And then 98. Yep. Okay, so we're reading the gigahertz and we're relatively stable. I don't see a problem now. Problem was the fuse was blown. Fuse blew because somebody put too much power through it. I know that Bob was trying to measure the output of his transmitter, his frequency of his transmitter. My guess is he connected this thing in such a way that he put too much power into it, blew the fuse. Alright, we are right now reading on channel C 149,999.97 kilohertz. 150 megahertz is the rough interpolation of that, but 149.99997 kilohertz. And as you can see, we are stable. We're not popping around as was reported, so problem was the fuse. So now just what do we do?